I'd like to get started. The first thing I think I need to say, which may be obvious, is that I am not Andres Taylor. The schedule still has his name on it. Unfortunately, he got sick just 2 days ago and couldn't make it. So I'm going to give you my take on performance improvements in Neo4j 3.2. I work with Andres. I'm currently the Cypher Team Lead, so I think I've got some useful things to tell you about the performance improvements we've made. First of all, I would like to tell you a little bit about myself. You can see where I'm coming from. I started working with Neo4j back in 2009, 2010 as a community member and later a customer. And one of the interesting things I got involved in was the Neo4j Spatial project and built an external library for mapping systems. And this involved importing very large amounts of data into the database. And at the time, I must say, there were things about Neo4j that I really liked, and there were things that I really didn't like. And one of the issues I had was that some things worked really fast, and other things definitely not so fast. I'm pleased to say that as of already a few years ago, not only did I end up joining Neo Technology and have become a core engineer, but all the performance problems that bothered me back then have been essentially solved. However, that doesn't mean there aren't things to fix, and there's still a number of areas that are definitely worth fixing, and I feel like in the last few releases we've seen several really great performance improvements. Since that time, this picture is the first Graph Connect in San Francisco. I was presenting spatial there, so this is a few years before I joined the company. Since joining, I've been focusing on Cypher, and Cypher is definitely the area I have the most to say about today. What I'd like to start with is this slide. This is a slide from the keynote this morning, the part where Philip presented performance improvements. So this is really the marketing take on performance. And there can always be a difference between what marketing says and what is really happening. So I'm going to go into more detail and we can see what's really happening behind the scenes so you can have a better understanding about where these numbers come from and what's really fast and what's not faster. This release has been a shorter development cycle than other releases, so as a consequence, we might not expect too much to happen, but I think we've got some pretty exciting things to show anyway, some areas that have been improved really dramatically. What's missing on the marketing slide, aside from uncertainty about the numbers, is that it's not clear at all really what these performance improvements are. How will it affect you as a user of the database? What queries are faster? Which ones are not faster? I'd like that to be my goal for today, to try and bring some clarity to that. It's a challenging thing to answer because it really depends on your databases. So I'll give you as much insight as I can into figuring out whether you think these performance improvements will really help you or not. But you're welcome to talk to me afterwards if you have any specific queries you'd like to know about. So let's switch out of marketing mode and get a bit more technical. This is my agenda. I found 5 things I thought I could present to you, 5 areas where we've made distinctive improvements to the performance of Neo4j. I've positioned them also architecturally. The diagram on the right there is a very simplistic layered architecture for what Neo4j looks like. We've got many diagrams like this. This one's very simplified. And as you can see, we've done performance optimizations in a number of areas. Deep down in the storage and kernel areas. We work on the Cypher runtime, work in planning to find better plans, and then one particularly interesting one, the Composite Indexes, which was a full stack implementation. One thing that's not clear in a picture like this is the level of complexity. So for example, that compiled in the tiny little box over there sounds like a simple thing. I'll tell you a lot more about that later because that's probably one of the most complex areas here. Let's go through these one at a time and see what we've got. The native label index. I think it's quite likely that most people don't even know that such a thing even exists or what it is. This is an index that makes things faster if you ask a question like, find all nodes in the database that are musicians, and you have a label called musician. So it will go to a special index that finds nodes by label. And this has been around for a long time, and it has been very good to have this. It's much faster than loading every node out of the database and checking the label. But we felt that this is an area that could be improved in performance. And so we built a ground-up implementation of a GB plus tree that was designed to work very well under concurrent read and write load. And because it was custom built just for our database, we thought it might perform a lot better than what we had before, which was Lucene. And it turned out to perform a lot better, especially for writes. In read loads, we find it's pretty much the same as before, but with write loads, we see some dramatic improvements. Particularly, look at the second set of results there, the one that says plus label at the bottom. This is a benchmark result where we are just adding nodes to the database as fast as we can. Every node has got one label. So we're adding labeled nodes. It's a pretty common thing when you build your data model. You very often will create your nodes with a label. And the difference there is about 3 or more times faster. In fact, just to glance back, 30 to 300% faster according to marketing. So that's pretty good. We're actually in that range. So our ideal case there, 3 times faster, is definitely aligned with marketing. The column to the right of that, that says plus schema. Slightly more complicated scenario. We create a node with a label, but this node is also going to get added to a schema index. That means it's got properties on it that are indexed in another index. So there's 2 indexes involved, one for the label only and one for the properties. So you can search later on for nodes based on their label and property. That one we see this, it looks like 50% by my eyes, but 30 to 50% faster there, that looks pretty good. That you should feel that difference. That's nice. Why is it not 3 times faster? The answer is very simple. The schema index does not yet use the GB plus tree. There's a lot of reasons for that. It's going to be quite challenging to move that into the schema index. But it is an opportunity for improvement. Because it's much more complex than a label, I think it'll take some time. So I'm not sure when. So we're seeing exactly this 30 to 300% improvement. That's really, really nice. We've got a whole pile of benchmarks like this, including the rightmost column, plus benchmarks with a large transaction size across clusters and many threads running, and they all show the same kinds of trends here. So we see this as a reproducible performance improvement in many scenarios, which is really great. The next one. Now this one is close to my heart because I was one of the key developers in this area. This has been a feature that's been requested for a very long time. We've always supported the idea that you can index a node by label and property. So you want to find a user by email. So find all users that have this email address. Common thing. And you can find users by multiple properties. You've always been able to do that. Find users by first name and last name. However, we could only have an index on either first name, last name, or 2 indexes. We couldn't have one that did both. So that's the new feature here. Small change to the Cypher syntax where you can now specify multiple properties in the create index command. No change in the Cypher syntax for actually querying the graph. So the Cypher planner will automatically look behind the scenes, find out what indexes you've got. If the query looks applicable to a composite index, it will use it. If it doesn't, it will use a single property index, if it exists. So it's going to make all of those decisions for you. You, as always, will just add the indexes you think will benefit your situation when you need to. There was a pre-existing core API schema for those that are working with embedded or procedures that already supported syntactically the addition of composite indexes. That is now working. But unfortunately, there's no support for querying composite indexes in the core API yet. It would be a pretty simple change if there's demand for it. So primarily think of this as a Cypher feature. The feature at the moment has a few restrictions. It doesn't work in every case you might imagine it could work. Primarily, you must have predicates in your where clause that are equality predicates for every property in the index. So the example there in the middle, match where first name equals Joe and last name equals soap. I have an equality check on first name and another equality check on last name. They must both exist in order to use a composite index on those 2 properties. In the benchmarks, I can explain why they must both exist. There is another set of scenarios under which you might expect things to work. For example, look at the bottom rows there. We can imagine that if you had an equality and an inequality, or an equality and an existence check, we could theoretically use the index. We don't do that yet. So that's another area for possible improvements at this point. We expect that what we've catered for here is the primary, most common use case where people care the most. So I'm looking forward to see how people react to this feature. Let's look at performance. There's a lot of things to say about this slide. Let's start by giving you a rough idea of what we're actually benchmarking here. We have a data model. It's a social network, a dating site. I think it comes from the Czech Republic. And it's got some million or so users in it and lots of relationship between them. So you can imagine these dating profiles are connected to people they know or are connected to in a big complex network. Also, what's very interesting about this is every profile has a different set of properties on them. Some properties, everybody puts information in. They always say their gender, their hair color, their eye color. These are properties that everybody fills in. Other properties they don't usually put on their dating profiles, like pets and children. And there were actually 40 or 45 different properties that we could play with here. So I've taken a selection of very commonly used properties and much less commonly used properties because it really highlights where the composite index makes the most difference. Look at the second and third rows there. Those ones have got predicates that say the second one's looking for a particular gender, a particular hair color, and a particular eye color. And the one below that for a particular gender and hair color. So these are quite simple, specific things that will trigger either a 2-property or a 3-property check. Both of them are improving our performance by 50% to 100%, 1.5 to 2 times faster than when we have no composite index. So it's a noticeable improvement, but it's not massive. The reason is because if you have a single index, you're still going to you're going to get the same number of results because everybody has added all of these properties to their profile. So these are high cardinality properties that everyone does. So the composite index helps, but not enormously. However, if you go down to, say, the fifth one, that's more than 3 times faster. It's also 2 properties, but it's much faster. Why is it much faster with 2 properties? Simply because it's low cardinality properties. Those properties are not often used. The index will be smaller, and it will respond faster. And this is actually an interesting factor, that the more properties you use in the index, the smaller it will get, if they are not dense properties. And also, low cardinality values will also increase performance. That leads to the top one, 9 times faster. That's fantastic. That's because that is a 5-property index with some low cardinality values. So this is I'm trying to cover the range between cases that we're going to see small improvements to cases we'll see massive improvements. All depends on the nature of your data, the nature of your graph. As with all benchmarks, you're going to have to try this yourself, try it on your data, see how it works. I'm pretty sure you're going to see numbers within the ranges that we are showing over here. Very exciting. The one outlier here, I don't know if you've noticed that, middle line, 74 times faster. It's so fast I had to change the X scale because it went right off the screen. That is nice. It's actually not just composite indexes. What we're seeing here is 2 different performance enhancements kicking in together that were introduced in 3.0. Composite index being one. The other one is a thing called nested index joins, which I don't have a slide for. So I think if anyone's really curious to know about the nested index joins and the massive improvements there, let's take it afterwards. I've got some examples we can talk about. But needless to say, there's more happening here that's than I've got time to show. Moving on. All right. Pretty cool feature. It's really technical, so let's take it in a historical context. This all started when Andres was at last year's Graph Connect San Francisco, and he was chatting with Max Damasi. And anyone knows Max? I think they will recognize him. He's a field engineer that's really concerned about performance. He spends a lot of time helping customers make things faster. And one of the things that he keeps stumbling across are areas where Cypher is slower than writing some Java code. So our goal in the Cypher team is to always get rid of those gaps. And he found a gap there where the users were interested in finding paths from one node to other possible nodes. And the query up there says, starting at Kevin Bacon, a particular node, find all possible related nodes up to a certain depth. So it's not a fixed end node, it can be many, many end nodes. The 6 degrees of Kevin Bacon question. So it's really reachability. What you don't care about in this query is all of the possible ways to get to that node. So once you've found that end node, you don't care about if it took 3 hops, 5 hops, and if there was 20 different paths, different ways to get to that end node. You only care that it is connected. So that's this type of query. And it turned out that the way Cypher was solving it, look at that match clause. The first line was being planned without regard for the second line. The first line basically says, find me all the paths. That's lots. In a big graph, if you make that var length very long, you could have enormous numbers of results. So it's going to create a lot of results, but many of those results are going to give you the same answer. Many of them will have the same end node. So you're actually doing unnecessary work. So the fix here is to say, if we see this kind of pattern and there's this distinct actor telling us we don't care if that actor occurs once or 20 times, we just need to know he's there. Let's try and reduce the solution space, not search every possible combination of the graph. And then so over the next few months, there was some interesting brainstorming within the Cypher team, and Andres and Johan worked on this and came up with a really great algorithm. Look at the results. I'm not going to explain the algorithm. You can take that offline. But it just reduces the solution space by recognizing cases where you don't need to search in a certain direction because you've already dealt with all of the combinations. But look at the benchmark, the results there. If your search depth is 1 or 2, it doesn't make any difference. But as soon as you get to a search depth of 3, that's not very deep. 6 times faster. That's really great. 4, 20 times faster. 5, 3,500 times faster. The marketing material said orders of magnitude, but we can definitely see it here. I'd love to see the 6 times. I think with the 6 times, we don't have numbers here because I don't think it finished for the old Neo4j. It was running for too long. So it's, this is the great feature if you've got that kind of query. Really nice. Right, this is the one that I said was big. There's a lot of history behind this project. It's been going on and off for the last 2 years. It's quite an ambitious attempt to produce an entirely new runtime that is really optimizing everything about how we run the Cypher queries. Because it's quite an ambitious project, it has taken time to really show results. There was support for this in 3.0, but it was something we didn't really market, and over the last 2 releases we've extended that. So now in 3.2 we feel like this feature is covering enough queries that it's likely to really help a number of people. But it doesn't cover everything. So my challenge right now is to try to give you a rough idea of what it covers and how much it's going to help you. That's really hard to answer because it really depends on your queries, but let's give it a shot. What we noticed in developing this is that we managed to get for 3.2 up to 50% coverage of the Cypher operators. So this is the low-level components of the Cypher runtime. So that's a decent coverage of the operators, but it doesn't really translate clearly to which of your queries will be supported. Because if you have a query that uses many operators, if only one of them is not supported, the whole query is not. So we looked at 2 of our main benchmarking suites. And in the LDBC suite, which is a pretty heavy-duty benchmarking suite, we got 18% coverage. That's quite okay, I hope, because that's a benchmarking suite focusing on complicated queries. So most of your queries may be more simple, have a much better chance of fitting in. And the Cypher benchmarking suite, where we've got some 350 queries. It's a very extensive one. also tends to lean towards edge cases and tricky cases where we, as developers of the product, care about performance, so we put them into our own benchmarking. So I suspect that out in the wild, we're going to get a higher coverage rate than that in your cases, you're probably going to feel these improvements more than we do, especially with simpler queries or queries that don't do too much. I've got some example queries that will hopefully give you some clarity there. And those examples are in the benchmark. So let's look at that. Performance. With the operators, it's very easy for us to measure that. 2 to 20 times faster. That's really great. With queries, it's a lot more subtle. I'm going to show you some numbers, and you can decide for yourself. We did quite a lot of extensive benchmarking of the operators. So I'm not going to go into too much detail with all of these operators and what they mean, but this is the 50% of the operators that are covered, and some of the really slow ones have been improved a lot, and some of the fast ones have been improved even more, so it's really helped a lot. It's hard to make sense of this chart, so change it to that. This is the relative performance, and we can see that everything is faster. The worst performance improvement looks like at the top there, maybe 2.5 times faster, and the best is sitting at 25. So this is quite nice. So in terms of the low-level components, we're seeing some pretty sizable improvements with this runtime. So that's really great. So we know we're on the right track. This is really helping a lot. Now let's look for Cypher queries. LDBC, quite complicated queries. There are only 13 or 14 queries in the suite that we looked at, of which 4 are covered. I'm not going to explain what these queries do. You can ask in questions afterwards if you want. The main thing is we're seeing here around about 2 times faster most of the time for these very complex queries. So it's not as exciting as what we saw with the operators, but this is still something that will impact your experience with Cypher performance. Now the Cypher benchmarking suite itself, this is a much more extensive suite ranging from very simple to very complex queries. And these are all the queries that were supported, the 15% of those 350 queries. What I was excited about when I looked at this is those queries look quite complicated. They're quite long. Many of them are truncated. They go off the screen. That's nice. So we're seeing support for the compiled runtime is reaching out to some quite complex queries, and hopefully that means you're going to experience this performance improvement. We also see a bit of a plateau in the middle there. Most of the queries are seeing about a 2 times performance improvement. That's great. So that matches what has been presented in other presentations. But at the bottom there, we see all of these queries that are going 4 times, 6 times, 8 times, 14 times faster. That's nice. That's really nice. And what I liked is that in that area where we're going much faster, there are a few somewhat complicated queries. So it feels like we're really on the right track. This is heading in the right direction. Hopefully, every release going forward, we're going to see better and better coverage and more improvements that will help everybody. All right, the last one. I think my timing is fine, right? So this one, I didn't even realize was a performance improvement. It was done by Andres. He just stumbled across this in the code while working on the composite indexes. Said, oh, here's a thing we should fix. Fixed it, and I didn't think about it again. But then I saw it on his agenda that he wanted to present this as a performance improvement. So I decided to do some benchmarking. I ran them overnight last night, and I've got them on the next slide. And I'm going to be interested to see how you react to that. But let me first explain what this is. Look at the first query at the top there. It is a query where we have 2 predicates with an and. We said, we require the first name to be a particular name, and we require the last name to be a particular name. We have supported that with index lookups forever. Typically, you pick one of those 2 and you do an index lookup on one and you filter on the other. And that's going to be fast. And now with 3.2, if you have composite indexes, even faster. So that's been well supported. But look at the second query. Here you have a predicate that says the first name must be something or the last name must be something. It's a very different thing. And you can't just combine those 2 into a single search. It's almost like the database has to be told, do one query, do another query, and concatenate the results. So it turned out that our planner didn't really solve it that well, and nobody really complained either, so it's obviously not a particularly common problem. It couldn't figure out how to do that, so it was simply doing a label scan. So it was finding all nodes with that label and then filtering with a filter that said it could be with this property or that property. That's the simple solution, but it does not perform well. So what we've done now is we've solved it with 2 index seeks, and we've actually combined it. We say, find all of them with that, with one index, find all of them with that, with another index seek, and you get it to work, and combine it much, much, much faster. How much faster? Let's have a look. There we go. So the red and the yellow are the 3.2 and 3.1 results. Let's start with the less exciting one, the top one, where it's only 5% faster. The reason for that is that gender and hair color, this is that same data set we were talking about before. Everybody's got it. It's there, so actually asking the label index is about the same cost as asking the schema index. Both of them are the same size. It's going to cost nearly the same. It turns out to be slightly faster to ask the schema index, so we've made a small improvement. But as soon as you have lower cardinality properties that are less common, of course the label index is not getting smaller, but the schema index is. Here's one where I ask for pets and children, pets or children, and it's 15 times faster. So I think this is, again, a case where it really depends on your data, but we're seeing that if your queries are of the right query or data is the right data, you can see some massive improvements over here. So that's very nice. This feature feels like one of those areas where we're just closing a hole. So Cypher is something that covers everything in capability, but doesn't cover everything in performance. And at the moment, it feels like we're just closing some of these last loopholes where we're not as fast as we could be, and this is one of those. Right, that's everything I have, except for that link, which I think could be interesting for people. It's the only resource I thought worth sharing. Michael Hunger has put together a nice list of operators and resources for deciding which compiled runtime components will support you. So if you have a query and you want to know if it'll work with compiled runtime or not, his resources are designed to answer that. So you can get a link for that afterwards if you want as well. We can take questions right here since it's the fika break coming up, so I don't need to move. It is basically almost the end of time, though. Do we have time for questions?
Probably since we have a fika break.
Okay. Are there any questions? Yeah?
Yeah, the compiled runtime, you said that if any one part of it couldn't be used in the compile time, it couldn't be used for the statement. Does that include sort of sub-clauses where you might use a with or something like that to pass on to the next part? Is it all that way? I mean, are you able to optimize on sub-clauses, for instance, compiling sub-clauses?
Let me repeat the question. You're asking that I had stated that if some part of a query was not supported by the compiled runtime, the entire query would not be supported. And the answer is yes, even for horizons like with. So if you have a query with some more subquery with, the entire query, the entire statement has to match. And that's something we're actually looking at a way to work around. So it may not be the case in the future, but at the moment that's exactly it. So if you do have a case like that, you might want to rewrite the query into 2 queries, for example, get one working on compiled and the other one not. Another point that I didn't make, which is worth mentioning at the moment, is that it's the default, so it was try the compiled runtime. You can also check whether it's using compiled or not in 2 ways, looking at the profile, also by specifying that you want a compiled runtime, Cypher runtime equals compiled matched, and if you do that and it's not supported, you get an error, so you can see that very clearly.
Do you think the width would make a good break for actually chaining together the combinations?
It would. The problem is only that the compiled runtime and the interpreted runtime are too different for us to mix and match, but we're looking at ways of bringing them together to hopefully deal with that. Any more questions? That one back there.
That's exciting stuff. Does the OR index scan work for labels as well as properties? Or because the one thing was I it's pretty slow doing, is this label or that label, but is this improved in this in 3.2 or not?
No, because the OR planning is just on those predicates. The label one's a separate thing. So that's not supported by this. Someone's back there, someone.
Yeah, I noticed a slight degradation in the write performance because of the index on the label. Would that degrade if we had multiple labels?
Are we talking about that first column?
Yeah.
So that first column, we are not adding any labels at all. This is just a raw node insert with no labels. And we don't yet know exactly what that degradation is. It's pretty small, but it is affecting everything there. The use case of creating blank nodes with nothing on it is a rare use case these days, so we're not too worried about that. It could be various things. We are looking into it.
Okay. Right. Thanks.
Any other questions? All right. So if you do have questions you want to take with me later on, I'm going to be here for a couple of minutes, then I'm going to go out to coffee, so you're welcome to come join me. Thank you very much.